Hey everyone, today we'll be having a look at question number 3835. Count subarrays with cost less than or equal to k. In this question, we are given an integer array nums and an integer k. And we need to find the number of subarrays such that the cost is less than or equal to k. The cost here is defined as max of the num between in the subarray, minimum in the subarray, multiplied by the right index minus left index plus 1. This is also indirectly referring to the length. Hence we can say that the cost is max minus min into the length, and we need to find the number of subarrays where cost is less than or equal to k, which is given to us in the question. Having a look at the example given, we have an array 1, 3, 2 and we are given a k of 4. Now, to analyze this question, one subarray would be 1 and the cost calculated here would be the maximum in this array is 1, the minimum in this array is 1, multiplied by indexes we have 0, 1, 2, multiplied by 0 minus 0 plus 1. This gives us 0, which is less than equal to 4. Hence this is a valid subarray. The another array we can have here is 1, 3. The cost here would be 3 since it's the max minus 1 into 2, which comes out to be 4. This is equal to k, hence this is also a valid subarray. The third type we can have is this, whose cost comes out to be 3 minus 1 into 3, which is 6. This is greater than k, hence it's not a valid subarray. These were all the possible arrays starting from 1. We move on to the next element 3. The cost calculated here is 0, which is valid. Next would be 3, 2. The cost calculated here is 3 minus 2 into the length 2, which comes out to be 2, again a valid subarray. And the last possible option is just 2, and the cost comes out to be 0, a valid pair. So we have 1, 2, 3, 4 and 5. Hence our output is 5. Now the brute force solution used here is choosing every L, choosing every R and computing the max and min. Now this is very slow because computing the subarrays would take O of n square and computing the max or min between them would take O of n, which results in a O of n cube, which is quite bad for a algorithm. So optimizing this a bit, instead of checking every subarray, we fix the right pointer R. We find the smallest left pointer L that keeps the cost valid, that always satisfies this equation. So considering all subarrays suggests that we need to use a sliding window. Now comes the problem, how to keep a track of maximum and minimum inside a window. The best way to doing that is using queues, monotonic dequeues. A very important concept in questions where we need to keep a track of either the maximum or the minimum in a particular sliding window type. These are either max dequeues or minimum dequeues. These store indices and not the value given in the array. For a max dequeue, the values decrease from front to back. And for a minimum dequeue, the values increase from front to back. A very important thing to keep in mind. Now let's understand the whole concept via the same example where we have nums. We start a sliding window. L initially points to the 0th index and so does R. L represents the left boundary and R represents the right boundary. Here are our two queues, the max one and this is the min DQ. Starting from R is 0, we first check our max and min DQs. If they are empty, we push the index 0, whose value is 1. Remember, we just stored the index in the DQ and not the value. I'm writing the value just for reference. So when R is 0, we check our max and min DQs, and since they are empty, we push the index. Adding values in both DQs happens from the last, and while checking the max or min values, we check the topmost values. So now calculating the cost at R is 0, the maximum being 1, the minimum being 1, results in 0, which is less than equal to 4, and hence this is valid. Now we move our R to 1, whose value is 3. We check at max DQ. The rule here is that we keep popping our max DQ from the back until the values are less than or equal to the new value. So the new value here is 3. We check from the back. Since 1 is less than 3, we pop it from the stack. Now since we have nothing else to pop and our stack is empty, we add the current index 1. This ensures that our max DQ is decreasing. For min DQ, we do the opposite. We pop from back until the elements are greater than the new value. Since the value at 0th index, which is 1, is not greater than 3, we simply push back the current R value, which is 1. This ensures our min index is strictly in increasing order. Now for R is 1, we have a window of 1, 3. The max, which we check from the front of the max DQ, is 3. The min, which we check from the front of the min DQ, is 1. Simply 3 minus 1, and the length comes out to be 1 minus 0 plus 1, which gives us a value, a cost of 4, which is equal to 4, and hence we increase our count. One important thing to keep in mind: we initially have our count or answer as 0, and then each time we increase the count by R minus L plus 1. The reason for doing this, all subarrays ending at R are valid. For example, if a subarray starts at L and ends at R, then subarray L plus 1 up till R is also valid. L plus 2 up till R is also valid. This is because while counting the cost, we have max minus min into L, length. The length decreases, there's a high chance that the minimum value may decrease too, decreasing this entire subtraction. In either case, the decrement in the length impacts the most, and thus the value would always be less than equal to k. In short, if the bigger subarray is less than equal to k, then each shorter subarray contained in it would definitely be less than or equal to k. This itself converts the O(n) square counting problem to O of n. Thus the count here is updated to 1, and then since the length L here comes out to be 2, the count here would be 1 plus 2, that is 3. Moving our window further to 2, we check the max DQ first. Remember, we need to keep it strictly in decreasing order, so we check from behind. The value of 3 is not less than the value at position 2, thus we simply push our current R value. We check our min DQ from behind. This needs to be strictly increasing, thus any value bigger than 2 needs to be popped off, And since 3 is bigger than 2, we would be removing 3. We then again check the topmost value. It's 1. Since 1 is less than 2, we do not pop it and simply add the current R value to the end. Now calculating the cost for R is equal to 2, the max value, which is at the starting of the max DQ, is still 3, minus the min value at the starting of the min DQ, 1, and the length R minus L plus 1 gives us a value of 4. Now since this is greater than 4, this is an invalid subarray. We need to decrease our window to decrease the cost. Thus, we would now be moving our L. Basically, now our subarray is too big, so we need to shrink it, and we shrink it from the left. So we move L to 1. Now, whenever we're moving our L, we need to check our DQs from the front. If previously L was the max or the min, we need to pop it out of our DQ. So since L is 1, we check the front of the max DQ. It is not less than L, hence we leave it as it is. We come on to the minimum DQ. Since the front value 0 is less than L or is outside the substring, we pop it out. And thus, this is our main queue now. This is the most critical point on why we decide to store indices and not the values in the DQs. Because if we are storing the values, we won't be able to distinguish between duplicate values, and we cannot detect properly if the element left the window or not. For example, for a substring which has 5, 1, 5, we don't know which 5 has been removed when the pointer moves. Hence, it is impossible to solve this without storing indices. Here, once we move our index L to 1, we know any index 0 at the front needs to be discarded. Now coming back to calculating the cost, the maximum value at the front of max DQ is 3. The minimum value now at the front is 2. The length 2 minus 1 plus 1 gives out cost to be 2, which is less than equal to 4. Hence this is valid. Since this substring is valid, each and every substring occurring from it is valid. Hence we update our count by the length, which is R minus L plus 1. The count becomes 3 plus 2, that is 5, which was the output earlier. Now in case you are still confused why we are increasing the count by the length, then when R is 0, the only possible subarray is 1. When R is 1, the possible subarrays are 1, 3, and fixing the right end, we increase the left to 3. These are the two possible subarrays, and hence we increase the count by 2 here. For R is equal to 2, the cost is greater, and hence none of the substring is valid, and hence we move L further. Now when we reach to L is equal to 1, we find another substring 3, 2 to be valid. And again we add the length to the count, because keeping R constant and increasing the left, we get another substring 2. So the 5 possible answers are 1, 1, 3, 3, 3, 2 and 2, which is what we had discussed initially. Trying to summarize a bit, we use DQs because without DQs we would need to calculate the max and min at every step, which gives us O of n. But here with DQs, we were able to find the max and minimum value instantaneously, which is O of 1 from the front, and the updates were also O of 1. For the max DQ, we keep only numbers that could still become the max later. Smaller numbers behind bigger ones are useless, so we delete them. Similarly, for min queues, we do the opposite. We keep only numbers that could still become the min later. Bigger numbers behind the smaller ones are useless, so we delete them. Reiterating, in a max DQ, if a bigger number appears which needs to be added, all elements in front of it need to be removed because they can never be maximum again. Similarly, for min DQ, it's the opposite. If a smaller number appears that needs to be added, all the elements in front of it need to be removed which are larger than it because they can never be the minimum again. Having a look at the code once, we are given nums and a k. N is the length of the array. We create a max DQ and a min DQ. A count or result 0 and our left window is initialized to 0. We start a for loop from a right window, r is 0, up till the length of the array, increasing it one by one. First, for every value of r, we need to update our max and min queues. So while our max queue is not empty and the value in the array at the last index is less than nums at r, remember we are storing indices in the DQs. So as long as we are getting smaller values, we remove the smaller ones and store a larger one. This makes the max DQ decreasing. When our DQ empties out or we reach a bigger number, we add the index r. Similarly, in min queue, while it is not empty and while we are getting a value greater than the current value at r, we keep on removing it. As soon as we reach a smaller value, we stop and we add a nums r. This makes sure our min DQ is strictly increasing. Adding the index. Now, we check the cost r minus l plus 1 into the max. We simply pick the first value from the max DQ and subtract it from the first value of the min queue. An important thing here is to convert it to long, as these multiplications can become huge for integer to handle. Now, in this while loop, we are checking if our cost is greater than k, we increment our L. If not, we simply add the length to the result. Now for incrementing our L, we need to make sure that L always remains less than or equal to R, a base case in questions where we are applying sliding window. And also, we need to remove from our max and min DQs any value less than or equal to L. So if the first value in max Q is less than or equal to L, we remove it. Similarly, in the min Q, if it is less than or equal to L, we remove it. And then we increment our L. This was the part where adding indices in the DQs is very important to avoid missing duplicates. And also one important thing, we need to first remove L from our DQs and then increment it. Incrementing it before and then removing from the DQs might end up in you making an error. So if we do not have a valid subarray, we increment L up till we reach 1. Once we have a valid subarray, we simply add its length, which reduces counting all the subarrays within the subarray. And then a for loop returns back to increment the R. And once the for loop finishes, we return back the result. I hope I was able to explain it as better as possible. For any suggestions, do comment down. Thank you.